Hi everyone, my name is Jonas-Koepping. I'm a PhD student at Monash University, and in the presentation today I'm going to be talking about the geometries and potential emplacement mechanisms of elongate finger-like intrusion geometries. And you may ask yourself how this links up to nickel, copper, and PGE deposits. And to answer that, we need to have a look at their characteristic geometries. So there's a range of host intrusion geometry of nickel, copper, PGE deposits, but they often have one thing in common, and that is that economic concentrations of metal sulfides often have elongate finger-like geometries, suggesting that magma flow processes are an important factor for trapping sulfide liquids. In some cases, also the hosting intrusion body has an overall finger-like geometry, like this tubular chronolith here, which is the Nebo-Babel deposit in Western Australia. The elongate intrusions I'm going to talk about in this presentation are a potential equivalent to these tubular chronoliths. So understanding their emplacement mechanism may also further our knowledge on the formation of tubular intrusions and our ability to explore for them. Over the last decades, researchers have shown that dikes and sills, so sheet intrusions, not always propagate as a continuous planar sheet, but that they can form elongate elements at their propagating outer margin. And these are the geometries I'm going to talk about in this presentation. In some cases, they can also form these groups of elements, and in 3D, it may look like this, so that there's an inclined limb. We can have an inclined limb at the outer margin. And what's interesting here in this case is that these elongate intrusion geometries coalesce to form a more continuous-like sheet. And the contacts of these elements form approximately parallel to the magma flow direction, so we can use them as a magma flow pathway indicator. There are two main different mechanisms that can lead to the formation of elongate intrusions. And the first group is non-brittle and brittle deformation mechanisms, and the other one is fracture segmentation. And on the next slides, I'm going to give a brief overview of these emplacement mechanisms. Starting with non-brittle deformation mechanisms, which would be viscous fingering. And viscous fingering, for example, or in general, describes an unstable displacement of a more viscous fluid by a less viscous fluid. And in the video over here, I'm going to show you in a bit, there is a blue fluid with a lower viscosity injected into a high viscous fluid. And we can see that the propagating outer margin becomes unstable and breaks down into these elongate finger-like geometries. But in a geological context, host rock fluidization can lead to this instability, because when we have host rock fluidization, then there is a contact between a lower or relatively low viscous magma, a higher viscous fluidized host rock, which then may become unstable to form these elongate finger intrusions. Another magma propagation mechanism is viscous indentation. And in this scenario, the magma rigidity is assumed to be greater or equal to the host rock rigidity, and shear stresses at the propagating tip overcome the host rock strength, which results in shear failure. In this case, magma pushed the host rock ahead, similar to a bulldozer. Coming to the fracture segmentation, again, we have two scenarios. One is stress rotation, and here a planar continuous fracture breaks down into n-echelon segments due to the rotation of the principal stress axis orientations ahead of the propagating fracture. In the second scenario, magma follows pre-existing weaknesses, similar, or for example, they follow pre-existing weaknesses with a lower tensile strength and a lower fracture toughness, for example, bedding planes. And in this scenario, magma exploits these pre-existing weaknesses, which can also result in elongate finger-like intrusions. In both scenarios, these elongate intrusions are vertically offset and form a step-like sill geometry. But let's move on and have a look at what these intrusions look like in seismic reflection data. So the data set we are looking at is located on the northwest shelf of Australia. It's the Glencoe survey, which images 5 sills. The intrusions are of mafic composition and of early Cretaceous age, and are emplaced into Triassic sediments of the Mangrove Formation, so sandstones and shales. The top of the Mangrove Formation here is highlighted in green, and here we have the sill. And there are some pre-existing structures in this basin, or at this emplacement depth, which are north, northeast, south, southwest striking fault plains, here highlighted in black. On the next slides, we're going to have a look at this sill here in the northeast of the survey. This is a two-way time map, and these tide contours at the eastern margin and the western margin indicate an inclined limb. So it's an elongate sill geometry with an inclined limb in the east and the west. On this amplitude map here, I also highlighted all the pre-existing fault planes. And we can see that there is a major bounding fault plane here in the east, which coincides with the inclined limb in the east. So the magma exploited this pre-existing weakness and the fault plane to form the bounding inclined limb in the east. The overall geometry of the sill is elongate channelized sill in the south and a circular sill in the north, with inclined limbs here in the east and also in the west here. On the amplitude map, there are these elongate features with a relatively lower amplitude in the grayish brownish color here. And they indicate the contact between different elements, which are mapped on this map. And as I mentioned earlier in this presentation, we can use the contacts to interpret the magma flow direction. And based on our observations here, we interpret that the sill is fed through this fault plane, because south of the fault plane, there is an overall magma flow direction towards the southwest, similar to the strike of the bounding fault plane in the east. And north of the fault plane, where the sill is not bound by an inclined limb in the west anymore, the magma flow direction is semi-radially towards the northwest. When we zoom into the northern bit of the sill, we can see that there are even minor amplitude variations here at the outer margin, with only a slight drop in the amplitude, and that's what we're going to have a look at on the next slide. So we're having a look at cross sections through the sill. One of the cross sections is located here in the center of the sill, where the sill is thick enough to quantify its thickness. The other one is located at the outer margin, where we cannot quantify the thickness of the sill because the sill is too thin. In cross-sectional view, so the thickness is plotted in blue here, and in cross-sectional view, these elongate elements thicken towards their center and then thin towards their lateral margins, where they can connect or coalesce with their neighboring elements. This point where they connect is highlighted by a drop in the amplitude, here plotted in red. And we can see this drop in amplitude in both cases, so for the thick and the thin area of the sill, which helps us to identify and map channelized flow and small scale elongate elements, even in the thin areas of the sill, where the sill propagates at approximately the same stratigraphic level. And saying this, we can redraw this map on the right, and the sill is actually composed of multiple elongate elements at the outer margin here. However, because we cannot quantify the small-scale host rock deformation and seismic reflection data, it is important to compare and link the cross-sectional geometries of these elements with a field analog, and where we can study the emplacement mechanisms. And the field analog we are studying is located in central Montana. So these are the Highwood Mountains of Montana. And specifically, we are looking at the Shonkin Sag laccolith. The Shonkin Sag laccolith is a mafic intrusion of tertiary age, which is emplaced into sandstones with thin shale interlayers of the Cretaceous Eagle Formation. The outcrop we are looking at is located here at the southeastern margin of the laccolith, and here's a schematic cross-section. We use the drone to collect images of this cliff face to create a photogrammetric model, which we then use to map and quantify host rock deformation mechanisms. The main magma flow direction in this area is towards the southeast, so the cliff face is approximately perpendicular to the magma flow direction. It's slightly oblique, but more or less perpendicular. On the next slide, I'm going to show you the photogrammetric model and how it looks like. And so this is the main cliff face here, with the sills in dark gray. And there's a gully between the second cliff face. So we have the main cliff face on the left-hand side here. And due to the gully, there's another cliff face inside of this main face here, and then another one outside. So we have three cliff faces where we can study these elongate intrusion geometries. And as I said, we also map the host rock deformation, and that's what I would like to show you in the next slide. I'm going to start with the host rock fluidization. This is a section from south to north, so it's an oblique section. But what we can see here is that's the intruding finger, or the magma finger, and the lateral tip of the finger. And the head of the finger, there is brownish orange intrusive material, which is softer and more crumbly than the actual intrusion. And we interpreted this material to be some frothy magma, which which can form at shallow emplacement depths due to magma degassing. In this frothy magma, there are also blobs of the solid intrusion, but what's interesting is that this frothy magma mingles with the host rock, and there are these clasts of intrusion in the host rock, and the contact between the frothy magma and the host rock is irregular shape, which is an indicator for host rock fluidization. Another indicator for host rock fluidization is the irregular shaped contact between the intrusion itself and the host rock. This, for example, is a top boundary of a finger. But there are other deformation mechanisms as well. For example, this minor thrusting of shale beds into the sandstone and cataclasite bands here in this area. Other host rock deformation we observed includes host rock buckling, folding, and brittle deformation, but also shear failure and the compressional regime between two fingers. When we zoom in here, we can see these this minor thrusting of host rock beds. We also observed wedging, so the host rock deflection at the sides of an intrusion, which indicates the magma propagation through a linear elastic fracture. And it is important to note that all these deformation mechanisms, including the host rock fluidization, are observed in the same outcrop at a meter scale, and in some cases even associated to a single finger. So the emplacement model we suggest for the fingers of the Shonkin Sag laccolith is that the fingers were initiated due to host rock fluidization. However, their propagation mechanism, so when they grow in length, may be different. And we assume that we have magma propagation through a linear elastic fracture, through viscous indentation, and through host rock fluidization. When fingers grow in width, in the compressional regime between these two fingers, we observe mostly the brittle deformation, folding, and shear failure then. As a last step, we were interested in having a closer look at the amount of host rock uplift above fingers. And for this, we again mapped fingers in cross-section. Here we have shear failure, we have some host rock fluidization at this finger, and we mapped the host rock thickness of some beds. And the host rock thickness varies up to 20 centimeters, so there is a host rock uplift of up to 20 centimeters. And compared to the finger thickness, we can show that up to 18% of the finger thickness during the emplacement was accommodated by host rock uplift. When there is only a narrow gap between the fingers, we interpret that the elastic deformation is potentially distributed over a larger area, and that's why we don't see a drop in the host rock in the uplift here between these fingers. And when these fingers grow in width, they can also coalesce, and they can form these continuous sheets. And that's similar to what we observed in the seismic reflection data. So we have a thickening towards the center, a thinning towards the lateral margins, where they then coalesce to form this continuous sheet. Here we also measured the thickness width aspect ratios, in blue for the field work, and red, this is the data plotted for seismic data, so in red and in black. And we can show that the thickness width aspect ratios are of approximately the same magnitude. So these geometries are self-similar over multiple scales. And we can compare the field work with the seismic reflection data. To conclude, we showed that even small-scale elongate intrusion geometries and areas of channelized flow, which potentially can contain sulfide liquids, can be identified and mapped using 3D seismic reflection data. So this also highlights the importance of 3D seismic reflection data, as it can increase our ability to explore for tubular intrusion geometries. The thickness width aspect ratios of the geometries we mapped in seismic reflection data and in the field are self-similar over multiple scales, so we can compare these different outcrops and the different data sets. And based on the observations we made in the field, we suggest that multiple deformation mechanisms were at play during the emplacement of fingers at the Shonkin Sag laccolith. And these emplacement mechanisms may also have changed over time, so their emplacement is more complex than a single end member model. As a next step, it is important to link the seismic data and field data with analog and numerical models to better understand the physics behind the emplacement of elongate intrusion geometries. And with that, I'm going to hand over to Uchi, who's using analog models to study the effects of solidification on the formation of channelized magma flow. Thank you.